Okay, I think it is time to continue our workshop and okay. And for today's session, we have 4 talks, and actually almost all of these talks are doing with some applications in coherence theory or blocks or Steiner system or designs. So some new results on this area will be represented by our speakers, and we also have one more talk on some results in domination theory of graphs. So our first speaker is Ivan Mogilnykh, who is affiliated with Sobolev Institute of Mathematics as well as with Novosibirsk State University, and his talk is about minimizing the number of blocks in some binary designs. So the floor is yours.
Thank you very much. I would like to thank Elena Valentinovna and all the organizers of this conference for inviting me. This is my joint work with Alexey Maryin, who is with Novosibirsk State University. A general outline of my talk is as follows. I will start with an introduction and I review some known results. Then I give some information about constructions of certain type of designs, giving small number of blocks. Then I move on to lower bounds on the number of blocks. And then I finish with an approach of handling the minimization problem for the number of blocks via integer linear programming. So a classic definition of simple design is as follows. A T nk lambda design is a point set of size n and a block set, which is composed by k subsets of the point set, such that every T subset is in exactly lambda blocks of the design. But in this talk, we consider so-called binary designs. What is a binary T and K design? It is also a certain point set and a block set, which is composed again by of some K subsets of the point set, such that every T subset is in even number of blocks. So this number is not a constant as in the classical definition. Well, these objects were quite known under many different names. They arise in combinatorics, various applications, also in coding theory. As a quick example, one might consider a so-called Pasch configuration, which is composed by these 4 blocks of size 3. We see that every point is in 2 blocks. So it is actually a binary 1, 6, 3 design having 4 blocks. So yes, as I have already mentioned, these objects are known under various names. Some of them are null designs. Some researchers also call them unit rates and many other. So in throughout what follows, I denote by dtkn the smallest number of blocks among all T and K designs with non-empty block set. And the main problem which is considered in this talk is as follows. Given these values n, k, and t, find the value for d, t, k, n. And the main result is determining these numbers, these values, for all t not greater than 3, any k, and sufficiently large n. So we all know that for classical designs, we have, for classical T designs, when T is not less than 2, we have some bounds on the number of blocks, such as Fisher inequality, but this definition is different, and many of those bounds do not hold in this case. So a little bit of history, and also some maybe some interconnection with coding theory. So actually we have a structure of a linear space on the set of all T and K designs. If we take as any the symmetric difference of any two such designs, it is again a T and K design. So these designs are in one-to-one correspondence with the code words of the binary linear code, which could be defined as the solution space of the homogeneous linear system. The matrix of the system is the Pilson inclusion matrix. So, and in coding theory terms, the minimization problem for the number of blocks in a binary T and K design is equivalent to finding the minimum distance of this code. One of the previous results is that the value dt t plus 1n is actually t plus 2. So when we have the difference between strength t and the size of block being just 1, the minimum value for the number of blocks is just t plus 2. It was proven by Wang Zhang and Liu, and independently by Potapov. So Wang Zhang and Potapov, they used mainly coding theory terms. Also, our previous report at Algebraic Graph Theory was given mainly in coding terms. In that report, we gave a solution for this minimization problem for t equal to 1 and 2. Well, if we speak about some rough bounds, those are as follows. D, T, K, M varies from t plus 2 up to 2 to the power t plus 1. And actually both bounds are sharp. So the solution for the case t equal to 1 is actually very simple. The minimum number of blocks in a binary 1 and k design is 3 when k is even, and 4 when k is odd. Well, starting from some n. And for t equal to 2, the picture gets a little bit more complex. We have more cases here. The first one is when k is 3. This is actually the case that was proven before by Potapov and Wang Zhang and Liu. And in this case, the minimum number of blocks in 2 and 3 design is just 4. These numbers gets larger 6 for k being odd, 7 for all k divisible by 4, and 8 when k is 2 modular 4. So I finish with the introductory section, and actually, if there are any questions, everyone is welcome to ask them. So you can interrupt me anytime. Okay, so as for the constructions, we have several different constructions. And all, mainly they are recursive. So we start with some well-known object and do some recursive operations. We start in the following construction. We start with 2742 Hadamard design in a classical sense. This design is a unique design. It has 7 points and 7 blocks. And just from the definition, we see that actually it is also a binary 274 design, in the sense that every 2 subset is an even number of blocks, and this is just 2 blocks. So what we can do next is do the following operation, so-called blowing up of the point set. We replace each point in the point set of the initial Hadamard design by a set by L points. And actually what we get is a binary 27L 4L design with 7 blocks. So the point set could be made could be made large. However, the block set, the size of the block set is kept the same, it's 7. So, one small intermediate conclusion that, unlike for ordinary 2 designs, there might be many cases when several distinct points in a binary T design belong to the same set of blocks. Okay, and also we can do some manipulations, further manipulations with the obtained design. We can add an extra point to every block. And actually, we can see that the property of being binary 2 design still holds. But the point set gets larger by 1, as well as the size of the block. And another manipulation is adding not 1 point, but 2 more extra points. And we add them in a way that if the point n+1 behaves the same as the point 1, in the sense that it belongs only to those blocks that the point 1 belongs. Whereas the second point belongs only to those blocks that do not contain the point number 1. So the resulting design has 2 more points, and the block set is increased by 1. Block size is increased by 1. Maybe I will give a little bit of alternative description for this process that uses the concept of incidence matrix. When we speak of incidence matrix, we speak of matrix whose rows are indexed by points and the columns are indexed by blocks of the design. And we have one if and only if the point I is in the block P, and zero otherwise. So I remind you the definition of binary T and K design. It is a design where every T subset is an even number of blocks. equivalent definition could be given in terms of incidence matrix. Every T rows of the incidence matrix have even number of common ones. This is the same as every T subset of the point set is an even number of blocks. So I consider the last manipulation that gave us 2n+2 design, but here we have n equal to 7. Just we consider the Hadamard design and add 2 extra points. So in terms of incidence matrices, the matrix on the top is the incidence matrix of the Hadamard design. We can see that the definition in terms of incidence matrices is fulfilled. Any pair of distinct rows have just 2 common ones. But we can do a little bit more. We can extend this matrix by adding a copy of the first row, which is the point 8, corresponds to point 8. And also we add the complement of this row. And we see that actually the definition of being a binary 2 design also holds for this incidence matrix. Any pair of rows still have even number of common ones. So the next construction is so-called doubling the blocks construction. It is a recursive construction which works for any initial binary T and K design. So we consider 2 copies of the blocks, and we add 1 extra point to all the blocks in the first copy, and we consider blocks with point n+2 in the second copy. And also, actually, this simple construction gives us a binary T+1 n+2 K+1 design. And also, it gives us an upper bound for the minimum number of blocks. So the minimum number of blocks in a non-empty binary T+1 n+2 K+1 design is not greater than 2 times the minimum number of blocks in a binary T and K design. So, so it is important to know the exact values for D, T, and K when T is small. So we actually have to work our way from T up to from small values of T up to larger values. One more construction is a so-called all subsets construction. This construction was mentioned in works of Potapov and Wang Zhang and Liu. We take all K subsets of K+1 element set. And actually, this is a binary T and K design with K+1 blocks in case when K minus T is odd. In particular, we get some upper bounds for the minimum number of blocks in some cases, but only for small values of K. Okay, as for lower bounds, the following structure, we have the following structural theorem, which is more or less close to the results to traditional properties of designs. So we take a binary T and K design D and denote by Di the set of all its blocks that contain point I. And by Di overline, I denote the so-called derived design. Those are blocks of Di without I. So in theorem 2, we have the following. If the binomial coefficient k minus j choose t minus j is odd, then a binary T and K design D is also a J and K design. So not always we have the property that a T design is a J design for J less than T, but in some cases this holds just from the parameters.
Oh, Ivan, what is the relationships between T and G? I mean,
yes, J is not greater than T here. Thank you. G is from 0 to up to T. Yes, so and actually in the second statement of the theorem, we do not really require this condition. It states that just this derived design is a T minus 1, A minus 1, K minus 1 binary design. And in particular, we get the following, well, more or less simple lower bound on D, T, and K, the iterative one. So third statement of theorem 2, if D is a J and K design and also J minus 1 and K design, then Ti, which is composed by all the blocks of D containing I, is a J minus 1 and K design. And the complement of Di to G is also a J minus 1 design. In particular, when K minus T is even, we have the following improvement of the lower bound mentioned in the second statement of the theorem. We have dt minus 1, K minus 1, and minus 1, and also dt minus 1, K, and minus 1. Also, there is among all these designs, we can especially consider universal designs. Those are designs that are actually I designs for all I from 0 to T. Yes, well, more or less simple inductive argument implies that the minimum number of blocks in a universal T design is actually 2 to the T plus 1, the upper bound. And there are actually some values of T and K when all binary T and K designs are universal. If we take K equal to T modulo 2 to this power, then any binary T and K design is universal. In particular, the minimum number of blocks, which we denote by DTKN, coincides with upper bound 2 to the power t plus 1.
Well, and what is the problem with k which is not of this value?
We are not able to use these properties. So
I see.
Some of these statements in this theorem, they do depend on some conditions when some binary coefficient, some polynomial coefficient is even or odd, and those could be explained when k is equal to t modulo this power. And so this is just a corollary of this theorem. Yes, so as some kind of intermediate stop, we have the following table. I'm sorry for tablica. So here we have bounds for d, t, k, n for a sufficiently large n. T is 3. We're focused on this case. So in some cases, we know 16 because 16 is 2 to the t plus 1. It is just the corollary, the previous corollary. We know exact value. Those are those cases correspond to universal designs. But in some cases, we do not know the exact value. We have some good lower bounds, again from this theorem too, that allow to narrow the gap from 13 to 14 when k is equal to 5, for example. But also we have bad lower bounds when they are small. We have pretty large gap. We are to decide the exact value here. So upper bounds are mainly based on some constructions like all subsets construction, doubling the blocks construction applied to a certain design. For example, this 14 is doubling the blocks construction applied to the point blow up of the Hadamard design. So what we do next is exclude some cases using combinatorial arguments. Those are for left values of odd k. Those could be explained combinatorially, but also we have some gaps that we were not able to describe to close using theoretical arguments, and we used computer. So I move on to the last section devoted to linear programming approach. And also it uses again the concept of incidence matrix and maybe a little bit its variation. Actually, we need not the incidence matrix, but the reduced incidence matrix. So I recall what is the incidence matrix. We have points and blocks that index the rows and columns of the incidence matrix. And we have 1 when the point is in the corresponding block. So what is the reduced matrix? The reduced matrix, the reduced incidence matrix is the matrix that is obtained from the incidence matrix in a way that we just exclude all repeating rows. So if a row is repeated exactly n times, we just leave only one of its copy. And also I have already mentioned that there are many cases when we have points behaving in a similar way in these designs, and we have to exclude this for simplicity. So as an example, simple example, I consider the point blow up of design D, which is 1, 2, 1, 3, 2, 3. So this design is again having 3 blocks total, but each point is now L times larger. Blocks are of size 2L. So the incidence matrix is just the repetition of this 3 by 3 matrix. We blow each point by L times, and the reduced incidence matrix is just one of these matrices. So the actually reduced incidence matrix obviously contains all the information from the of the contained in the incidence matrix. So in a sense that if A prime is a reduced incidence matrix, then there exists a positive integer vector Z such that Zi prime is k times rho, and by taking the I copies of the row of the ith row of the reduced incidence matrix, we just reconstruct A. So with this regard, we can consider the integer problem 1, which is as follows: given a matrix M, find a solution for this system of linear equations where Z and K are positive variables. So we will solve these problems for some matrices that are in general more larger than the set of reduced incidence matrices, but because we are searching for the reduced incidence matrices. So some more properties. If A is the incidence matrix of a binary T and K design, A prime is the reduced incidence matrix, then any T rows of A have even number of common ones. We have mentioned this already, but actually when we exclude some of the rows and consider the reduced incidence matrix, this property is also true. So any T rows of the reduced incidence matrix also have even number of common ones. And also this reduction process doesn't alter the property of having pairwise distinct columns in the matrix. Also, they have to be non-zero. One more property is that any row of the reduced incidence matrix got to have at least D, T minus 1, K minus 1, N minus 1 design. D, T minus 1, K minus 1, N minus 1. So this is the lower bound on the number of ones in any row of the reduced incidence matrix. This follows from the definition of the incidence matrix. So what we do is we search for reduced incidence matrix based on these last 3 properties. We recursively reconstruct some matrices, and then we do some kind of check-ins. Well, some reduction should be made in order to reject matrices that could be obtained using rows and columns permutation. We used NOTI-based function canonical labeling. A canonical labeling is a complete invariant, and it's actually just a graph. So all the computation was done in magma. Okay, so as a small example, I demonstrate the search for parts of the search for binary 2 and k design when k is even. Theorem 2 implies that the number of ones in any row of the incidence matrix has to be at least this value, which is 4. Yes, so we start our search. We fixed any first row with at least 4 ones. We have some cases here. Well, suppose this will be this row. In the second level, we have to pick a row in the matrix that have even number of common ones with the first row. And also we have to reject matrices given the same canonical labeling graph. All these obtained matrices will form the list which we call list mat. So every time list mat is in the beginning of the level is the number of level times 7 matrices. So after the second level of this iterative process, one of the matrices in list mat is as follows. We see that we have no contradictions here. Any 2 rows have just 2 common ones. Then we continue our search. At the level 4, in the beginning, we have list mat, which is composed by 3. Something is wrong here. Level. Something is wrong with numeration here of the levels. So at the beginning, the list mat is composed by 3 by 7 matrices. After appending a row, one of the matrices is as follows. So we see that this matrix is actually a part of the incidence matrix of the Hadamard design, but still we have to do checking for this matrix. For this matrix, we do, for all matrices, we do 2 checkings. The checking A is just checking that all the columns are pairwise distinct and not 0. And the second checking is actually launching the integer problem 1. And if the matrix passes both checks, then we keep it in a special list of possible reduced incidence matrices. We see that this matrix do passes checking A. All of its columns are pairwise distinct and non-zero. As for the integer programming problem, the result is negative. If we consider this system where M is this matrix, it has no solutions because the rank of M does not equal to the rank of the extended matrix. So we should not keep this matrix in our solution list. We just keep it in the list mat. We do another appending of rows and so on. So the search was done for t equal to 2 for even k. Actually, these cases are very different, even k and odd k. Odd k could be finished by some theoretical arguments. For even k, we require the help of the computer. So this list mat, which is composed by matrices at each level, was actually quite big. It was 17,000 when we excluded when we enumerated designs having 11 blocks. Still, only one of the matrices passed both checks, A and B, first and the second check. And actually, the result of the computer search for binary 3 designs is as follows. The only reduced incidence matrices for binary 3 and k designs with even k, when k is at least 5, having not more than 11 blocks, are actually the designs, just the incidence matrices that we have already known. Those are incidence matrices of all subsets constructions for k equal to 6, 8, and 10. So we have just 3 sporadic designs for k equal to for even k. So also we did a little bit different, a little bit in a different way. We did a search for binary 2 and k designs for k at least 4, and we listed. So in this search, we were focused on listing reduced incidence matrices, not just matrices that could be possibly reduced incidence matrices, but on the matrices that are really reduced incidence matrices. For 6 blocks, we got only 2 reduced incidence matrices. For 7 blocks, we have 3 reduced incidence matrices, and those actually describe the constructions that arise from Hadamard design. When we had Hadamard design, we did point blow up and did some manipulations. The number of reduced incidence matrices grow with the number of blocks. For 8 blocks, we have 20 reduced incidence matrices, 30 for 9 blocks. For 10 blocks, situation gets a little bit difficult for the computer. We have at least 15 levels. The search was dumped. We had over 200,000 matrices in the list mat, and we have very many reduced incidence matrices, at least 600.
Ivan, may I ask you?
Yes.
So in the previous cases, smaller cases, 6 blocks, 7 blocks, and so on, how many matrices do you have in the list mat in that cases?
Oh, actually, I don't think those are exceed say 5,000 for 9 blocks.
5,000.
Yeah, so this 10 blocks is a difficult case already.
I see.
Yes, and so actually even for 2 designs for 10 blocks, list mat is already very big. Actually, situation here is more difficult than for binary 3 designs when list mat was very, well, relatively small, 17,000. So I remind you our intermediate picture for when we had some gaps for t equal to 3. Some gaps, as I have already mentioned, could be closed using theoretical arguments when k is odd, but for even k, we used the search, which excluded all, closed all the gaps. So all the upper bounds that we had in this on this slide are actually obtained. So the result is the following theorem. For any case starting with some n, which depends on k, the minimum number of blocks in a non-empty binary 3 and k design is as follows. It is 5 when k is 4. It is 7, 9, or 11 respectively when the size of block is 6, 8, and 10 respectively. It is 12 when k is even at least 12. It is 14 when k is congruent to 1 modulo 4, and 16 in the remaining case. This is it. Thank you.
Okay, thank you very much for the nice talk. Are there any further questions to the speaker, to Ivan? Okay, I have one question concerning interlinear programming approach. I'm just wondering, which kind of problems do you have with this approach when you try to apply to minimizing the number of blocks in this problem?
Well, so that just could be described as finding a solution for this system of linear equations when the variable vector are z, and also one more positive variable is k. So Magma could, well, answers if there is a solution or not. And if there is a solution, it gives one solution, but actually there can be infinitely many solutions. But we are satisfied with at least.
We are satisfied with just one solution. I see. Well, actually, I like this approach. Well, it is not the first time for you to apply interlinear programming to understand what is between the result. If you cannot obtain some combinatorial approach, then you can use this interlinear programming approach, right? Yeah. So it is interesting enough. Yeah. Well, but I have never seen such kind of approach in other projects. Are there any researchers using this approach?
Well, it is quite popular for coding theorists. Many of them use interlinear programming. I got involved with this when I first heard that it is possible to find some interesting equitable partitions using integer programming approach. It works well for searching for equitable partitions. The person that mentioned it was John Bamberg. In his blog, he mentioned it, that actually linear programming solvers work quite well for finding equitable partitions. But in this case, we aim at certain designs, binary designs, using integer programming approach.
Yeah, it is interesting. I know one interesting graph theoretical problem where this approach was used to get and to find some bounds, low and upper bound for the diameter of graph. So it is really very, very nice. Okay, are there any other questions to Ivan? Well, if not, then let us thank our speaker again. Thank you. Thank you very much.